Given the first derivative f prime of x equals x to the negative 2/3 times x minus 1, find the location where f has local maxima, local minima, any inflection points, and sketch the graph. The first derivative will tell us whether the function is increasing, decreasing, and any local extrema value. The second derivative will tell us any inflection points and the interval where the function is concave up or concave down. In this case, we are not given the function f of x, but we are given the first derivative. The first derivative is 0 when x equals 1, and it is undefined when x equals 0. To see this, we rewrite the first derivative as 1 over x to the 2/3 times x minus 1, which is x minus 1 over x to the 2/3. We see that this derivative is 0 when the numerator is 0 when x equals 1. So this is when f prime of x is 0. And it is undefined when the denominator is 0, but the denominator is 0 when x is 0. And so we have two critical points for the function f. One is x equals 0, and one is x equals 1. We then construct the sign chart for f prime of x. The cut points are 0 and 1, although 0 is not in the domain of the function f. We then use the test point in each interval to determine the sign of the entire interval, the sign of f prime. From negative infinity to 0, we use negative 1 as a test point. From 0 to 1, we use x equals 0.5 or 1/2. And from 1 to infinity, we will use x equal 2. We plug these into the first derivative, f prime. F prime of negative 1 is negative 1 minus 1 over negative 1 squared cube root. This is minus 2 over a positive number, which is negative. So f prime is negative from negative infinity to 0. We then plug in 1/2 into the first derivative, and we have the numerator is x minus 1, so 1/2 minus 1, and the denominator is 1/2 raised to the 2/3. The numerator is a negative number, and the denominator is positive, and so we end up with a negative sign for f prime. And then we plugged in 2 into f prime. 2 minus 1 over a positive number, which is 1, and so f prime is positive. We see that the function is decreasing from negative infinity to 0, and then decreasing again from 0 to 1. It then increases from 1 to infinity. Because of this, f has a local minimum at x equals 1, and that local minimum value is f of 1. f of 1 is 1 to the negative 2/3 times 1 minus 1, and so this is 0, and that is the local minimum value, and it occurs at x equals 1. Next, we find the inflection points by finding the second derivative. F prime is given. To find f double prime, we would need to use the product rule. The derivative of the first factor is minus 2 over 3x. Negative 2/3 minus 1 is negative 2/3 minus 3/3, which is minus 5 over 3, times the second factor, and then we plus keep the first factor, x to the negative 2/3, times the derivative of the second factor, which is the derivative of x minus 1, or just simply 1. We then factor out x to the negative 5 over 3, because that is the lowest power in the factor x. We end up with minus 2 over 3, x minus 1 in the first term, and if we have x to the negative 2/3 and we factor out x to the negative 5/3, then this is x minus 2/3 minus negative 5/3, which is x to the negative 2, and then plus 5 is 3. 3 over 3, so it is only x. Simplifying this, we have 1 over x to the 5/3, and then negative 2/3 x plus 2/3 plus x. But negative 2/3 x plus x is positive 1/3, and so the numerator is 1/3 x plus 2/3, and the denominator is x to the 5/3. This second derivative is undefined when x is 0, and the second derivative is 0 when the numerator is 0, or 1/3 x plus 2/3 equals 0. This is 1/3 x equals negative 2/3, and so x equals negative 2/3 times 3 over 1, which is minus 2. And so the cut points of the second derivative are 0. We can't use 0 because 0 is not in the domain of the function, and negative 2. We then use a test point in each of the subinterval to determine the sign of f double prime in that interval. From negative infinity to negative 2, we will use negative 3. From negative 2 to 0, we will use x equals negative 1, and from 0 to infinity, we will use x equals 1. And we plug this into the second derivative. The second derivative, if we factor out 1/3 in the numerator, then we would have x plus 2 times 1/3 in the numerator, and the denominator is x to the 5/3. If we plug in negative 3 into the second derivative, then the numerator is negative because negative 3 plus 2 is negative 1 times 1/3, which is negative, and negative 3 raised to the 5th power, it is still negative, and so negative over negative is a positive number. F double prime is positive from negative infinity to negative 2. We then plug in negative 1 into the second derivative. Negative 1 plus 2 is positive, and negative 1 raised to the 5th power is negative, and so on the second interval, f double prime is negative. And if we plugged in 1, we have 1/3 times 1 plus 2 is 3 positive over 1 raised to the 5th power is positive, and so f double prime is positive. From here, we see that the function concaves up from negative infinity to negative 2, and then concave down from negative 2 to 0, and then concave up from 0 to infinity. Because f double prime changes the sign at x equals negative 2, we have an inflection point at x equals negative 2, and another inflection point at x equals 0. We now combine the sign charts for the first derivative and the second derivative and sketch the graph of the function f. Since we are not given the function f of x, we have no information about the y value, and so we just simply put the x-axis down here just for reference. But we still need to label all of the cut points. They are negative 2, 0, and 1. Negative 2 and 0 from the second derivative, and then 0 and 1 from the first derivative. From negative infinity to negative 2, f prime is negative, so the function is decreasing. F double prime is positive, so the function is concaves up. From negative 2 to 0, f prime is negative, so the function is decreasing. F double prime is negative, so the function is concave down. From 0 to 1, f prime is negative, so the function is decreasing. And f double prime is positive, so the function is concave up. From 1 to infinity, f prime is positive, so the function is increasing, and f double prime is positive, So the function is concave up. Armed with this, we will put in the shape of the graph. On the left-hand side of -2, the function is decreasing and concave up. That is a decreasing and concave up shape. From -2 to 0, the function is decreasing and concave down. But remember that when x equals 0, the function is not defined and f prime is not defined. So this means at x equals 0, we have the vertical tangent line. When we sketch the curve that is decreasing and concave down, we want to show there's a vertical tangent line at x equals 0, and so it should be steep at x equals 0. But this is still decreasing and concave down. Similarly, from 0 to 1, we want the curve to be steep at x equals 0 to reflect that it is a vertical tangent line at x equals 0. From 0 to 1, decreasing and concave up. And then from 1 to infinity, it should be increasing and concave up. Make sure that it is clear that the curve is increasing or decreasing, concave up or concave down. This is only one of the many possible sketches of the graph of the function f that has the given derivative f prime of x.